All right, this is the last video for Unit 1, Transformations, and it's going to be over piecewise functions. So the instructions say, carefully graph each of the following, identify whether or not the graph is a function, then evaluate the graph at any specified domain value. Okay, so we have our first piecewise function is going to be two pieces of two linear functions, two different slopes, different y-intercepts, all that good stuff. So my suggestion for this is when we are graphing these, start wherever the breaking point is, okay, or where the two functions will either meet or at least end and or begin, okay? So let's start with the first one. So I have x plus 5. So at x plus 5, I'm going to want to start with the input of -2 because I want to see what these two pieces are doing as we approach -2. So I'm going to start with -2 here. And because it's specifically for x is less than -2, I'm going to go -3, -4. So a lot of students ask, why are we using -2 when it doesn't actually equal -2? Why don't we use -3? Well, my question is, what about -2.5 or -2.3 or -2.0001? This piecewise, this piece of this piecewise is responsible for those values as well, and those are all greater than -3. So we need to use the -2 so we can at least see what is this piece doing as we approach -2. So plugging in -2 into this, we get +3. So now we can account for that less than, it's not equal to, by rewriting it as an open circle. So we'll do -2, +3. So this shows that the function is approaching that value, but it's not actually going to equal that value. So now -3 plus 5, we get +2. And then -4 plus 5, we get +1. So -3, 2, -4, 1. Now you could have just used the slope. It has a slope of 1, so going in the negative direction means we're going to go down 1. And we'll go ahead and draw this out. All right, now we're going to switch gears to the second one. So we have -2x minus 1. And this is for any value that is greater than or equal to -2. So again, I want to use -2 because I want to see what is going to be the relationship for these two pieces at -2. When I plug in -2, I get +3. And then because we're going greater than, we want -1 and then 0. If I plug in -1, I get +1. Plug in 0, I get -1. So -2, 3. So we'll fill in that circle there. And then -1, 1. And then 0, -1. So we have that slope of -2. And I'll stop it there. Okay. So now, is this a function? In previous courses, you used your vertical line test. This will be the only unit that we can use the vertical line test, all right? So if I scan across this, I can see that at no point will more than one output be responsible for each input, all right? So this one is a function. My next question is it continuous? Can I trace this without picking up my pencil off of the iPad? And the answer is yes. So it is continuous. So a function can be continuous or not continuous, okay? So just keep that in mind. Just because it is a function doesn't mean it has to be continuous. All right. Now evaluating f of 3. For f of 3, we want to use the piece for when x is greater than or equal to -2. So we're going to use -2x minus 1. So -2 times 3 minus 1 is equal to -7. F of -4, we'll use x plus 5, and we already solved for it, so it's going to be +1. F of -2. Usually I would say just focus on the one that it is actually equal to -2, but because we ended up with both of them being the same, we can use either one. Well, use the bottom one. but graphically you can use that point at 3 as well. Okay, next one. So with this one, we'll have 4x minus 2 and negative x over 3 plus 4. So let's start with the first one like we did before. So we'll have 4x minus 2. Where these two pieces relate is going to be at x equals 2. So I'll start with that point. And then this first one is specifically for when x is greater than or equal to 2. So I'm going to go 2, 3, 4. When I plug in 2, I get 6. Plug in 3, you get 10. Plug in 4, you get 14. So we'll have 2, 6, 2, 3, 4, 5, 6. And it is inclusive because it says x is greater than or equal to 2, so I can include that. And then it looks like this table can't fit the rest, so I'm going to hit halfway to show that the slope is 4. That's okay. Because really, we don't really care what's happening beyond this point. We want to know what's happening here with these two functions. All right, so now we have negative x over 3 plus 4. Again, we want to start at 2. Even though it's not equal to 2, I want to see what is this piece doing as we approach x equals 2. And then we're decreasing, or I'm sorry, we're going less than, so we'll decrease. So we'll have 1 and 0. All right, when we plug in 2, we get negative 2/3 plus 4. Y'all don't get a calculator of this unit, so you might have to do these fractions. So create a common denominator. So we get 12 over 3, which is equal to 10/3, which gives us 3 1/3. So a little above 3. So we'll have 2, and then a little above 3, and this will be an open circle because it's non-inclusive at 2 for this piece. If we plug in 1, we get negative 1/3. Again, we'll do 12/3. So we end up with 11/3, which is going to be 3 2/3. So just a little bit higher. And then if we plug in 0, we get 4. So no fractions for that one. All right, this is linear. It just has a slope of negative 1/3. So it's going to continue in this direction. All right, is this a function? So the question is does it pass the vertical line test? Well, if I scan across, at no point does the function hit my pen twice at once. So that means yes, it is a function. Now the question is it continuous? Well, if I trace my pencil, I get to 2 and I can't continue with the rest of the function. I have to physically lift it up and then go up and retrace. So the answer is no, this is not continuous. And this is an example. This is showing that one can be the other. Okay, so yes, it's a function, but no, it is not continuous. When I plug in f of negative 4, I want to use the left side. So we're going to use negative x over 3 plus 4. So I'll go ahead and plug that in. So we'll have negative 4 over 3 plus, I'm going to use the 12/3 again. And then I have 8 over 3, which will be 2 2/3. For 8, I want to use the function when x is greater than 2, so 4x minus 2. So we'll have 4 times 8 minus 2, which is equal to 30. And then for 2, again, I have 2 in both of my tables, but specifically the 4x minus 2 is where it's actually x is equal to 2, so I'm going to use this value. So when you plug in 2, we get 6. All right, next one. This one has 3 pieces. All right, this is pretty common, seeing 3. You rarely will see 4, but usually mostly you'll see 2, sometimes you'll see 3. For this one, we're going to start with negative x plus 4. And let's follow the same process. This is for when x is less than or equal to 0. So I'm going to start with 0 and then go -1, -2. That should be enough. All right, if I plug in 0, I get 4. Plug in -1, I get -1. So that's 1 plus 5. And then we plug in -2, we get 6. All right, so we have our y-intercept, which is at 4. It's inclusive because it says x is less than or equal to. -1, we're at 5. -2, we're at 6. If you don't need the table, then don't use it. You could have just done, oh, okay, this has a y-intercept at 4. The slope is -1, so I'm going to go up towards the left. So the table is just there since we've been doing transformation tables and whatnot. All right, the middle part. We have x minus 1 squared minus 2. So this will be a parabola. And we're going from 0 to 3. So I'm going to use every single integer in there. So 0, 1, 2, 3. The math won't be too bad. If I plug in 0, I get -2. That's a lie. If you plug in 0, you get -1 squared, which is going to be 1 minus 2, so we get -1. Plug in 1, we get 0, so -2. If we plug in 2, we get the same thing as 0, so we get -1. If we plug in 3, we get 3 minus 1, which is 2. And then 2 squared is 4. 4 minus 2 is 2. All right, so if we sketch this one, we are at 0, -1, non-inclusive. And then 1, -2. 2, -1. And then 3, +2. And that is inclusive. Okay. And then the last one, it says 2 for when x is greater than 3. So for 2, that means every single value that is greater than 3 for x is going to be 3. And it's non-inclusive, so I'm going to show that by drawing a circle around that. Okay, is this a function? It does pass the vertical line test. So at no point is there more than one y value for one x value. The next question is it continuous? Well, based on what we did with the last one, the answer is no because of this break here. If these were connected, then it would be, because this is continuous here. But it's not. There's a break, so the answer is no. F of -2, we already solved for that. So at -2, we got 6. F of 0, we also solved for that. We did it twice, but it's inclusive with the -x plus 4. So I'm going to use that value. So it's going to be 4. And then f of 5, I didn't solve that one yet, but 5 is greater than 3. So that means any value that is greater than 3 will have a value of 2. And the last one. All right, this is the first one where we've had a rational, so we want to check this one out. So we have x minus 1 divided by x squared minus 1. We need to rewrite this and see if we can find any attributes. So x minus 1, we have a difference of squares in the denominator, so we can rewrite that as x minus 1 times x plus 1. From here we have a common binomial, so we can cancel those out. So we'll have 1 over x plus 1. So this will be the first one that we can do. So we'll have 1 over x plus 1, and we'll just pick 3 values for that one. So this one is going to start at x is less than or equal to 2. So that means we'll start at 2, and then we're going to decrease or go down. So we'll have 1 and then 0. Plugging in 2, we can use the simplified. All right, these are equivalent. You don't have to use the x squared version. So we'll plug in 2, we get 1 over 2 plus 1, which is 1/3. And then 1 over 1 plus 1, which is 1/2. And then for 0, we just get 1. So this is when x is less than or equal to 2, so it'll be inclusive. So at 2, we'll be at 1/3. And then at 1, we'll be at 1/2. And then at 0, we will be at 1. Now, if we look at this, we canceled out x minus 1 in the top and the bottom. So that means that x equals 1, there is going to be a hole. And that hole is going to be located at 1/2. So when I come back to my graph, I'm going to redraw this as an open circle, because that is going to be a removable discontinuity there because we canceled out that factor. Also, this is a rational function, and all rational functions have a vertical asymptote and a horizontal asymptote. With this one, your horizontal translations will change your vertical asymptotes. So our vertical asymptote is going to be at x equals -1. The horizontal asymptotes are changed by vertical translations, which this one doesn't have. Technically, it's +0, which means our horizontal asymptote is going to be at y equals 0. So at x equals -1, we have our vertical asymptote. And then at y equals 0, we have our horizontal asymptote. So now we can see where this curve is going to approach on this direction, but it's going to stop at 2 because of my domain restriction. Okay, we do not go past 2. Okay, so this is technically 1 over x. It started as x squared, but when we simplified it, it's 1 over x. So that's what we're going to use as our model parent function. And for this one, you have a curve in quadrant 1 and quadrant 3. And it's going to have that rotational symmetry, so the second curve is going to be down here. You can also test a point. Like if you plug in any value that's less than -1, you're going to get a negative output, which means that curve has to be below the x-axis. All right, so a lot going on in that one, but it's just attributes that we talked about before. The second one is going to be x minus 3 squared. And this is for when x is greater than 2. So we'll do 2, 3, 4. Now something I need to go back and fix is that that first piece only exists up to x equals 2. So my horizontal asymptote is not going to exist past that value. So it'll stop here. So my horizontal asymptote and that whole function stops at x equals 2. So in class I made that mistake, so I apologize for that, but I will talk about that tomorrow when we review for the test. When we plug in 2 into this, we get 2 minus 3, which is -1 squared, so we get 1. Plug in 3, we get 0. Plug in 4, we get 1. So at 2, that is non-inclusive, so that's going to be 2, 1. So do an open circle. At 3, we'll be at 0. At 4, we will be at 1. So there's that parabolic shape. So -4, when x is equal to -4, we're going to use this, the first piece. So we'll have 1 over -4 plus 1, which is equal to -1/3. F of 0, we found that already with the first one. That's going to have an output of 1. And then f of 3, we found that with the second one. So that's going to be 0. And then something I missed is this a function? This is a function. Every single x value has at most one y value. Even though we have the hole and the asymptotes, this is still a function, all right? It's just in order for it to be a function, one x value cannot have more than one y value, or it can be absent. Is it continuous? With that asymptote, definitely not. The vertical asymptote. All right, so in calculus, certain operations cannot be performed on the absolute value function. Therefore, there needs to be another way to represent such functions. So once you get to calculus, you're going to see absolute values a lot more, and there's going to be some different manipulations that you'll learn in that course. So for this one, it says sketch a graph of f of x. So with this one, I can see that inside we have a horizontal translation of -2. So I'm going to put that point on -2. And then the slope has a value of 1. Now, usually this would go this direction, but because it is a absolute value, it's going to go in the positive y direction. All right, so thinking of the graph as two pieces, at what point does the graph change from one piece to another? The graph changes at x equals -2. And that's because of that horizontal translation in there. It is going to change at x equals -2. If the exact point was not visible on the graph, how would you identify it? So take whatever is on the inside of the absolute value, set it equal to 0, and solve for x. So if we had 3x minus 8, and I wanted to find out, okay, where are the two pieces changing, I would take this and set it equal to 0, which means the two pieces will change at x equals 8/3. So whatever is on the inside of the absolute value, set it equal to 0 and solve for x. So by setting the expression in the absolute value equal to 0 and solving for x. All right, use your answer from number 2 for the following. Write an equation that represents the piece to the left of that point. Okay, so the piece to the left, we can see that the slope is negative. Okay, it should be -x or -1x to be more specific. But how do we write the correct function for that piece? Well, if we take x plus 2, I can technically rewrite this as x plus or minus x plus 2. That covers any possible functions that we want to look at, okay? So these two pieces, actually let me do equals. These two pieces are going to look like this. We have a positive x plus 2, and we also have a negative x plus 2. But particularly for the left, you can see that the slope is negative. It's -1 all the way down. So this piece has to have the function that is going to have that negative slope. This one doesn't have a negative slope, it's positive. But for this one, if I were to distribute that -1, that would give me -x minus 2, okay? So this is equal to, whoops, that's equal to -x minus 2, so I can see that negative slope. Now this only happens up to x is equal to -2. All right, so I'm going to set my domain restriction as x is less than -2. So this is what you would want to write for that piece on the left side. You can do either this one or this one, it doesn't matter. However, you will see it distributed, and sometimes you won't, so you have to at least recognize both. Now it says write an equation that represents the piece to the right of that point. So all that's left is this one, and it's because the slope is positive, I want the positive x, and it has that y-intercept at +2, so it aligns with it pretty well. Well, it aligns with it exactly. So that means we have f of x is equal to x plus 2, and the domain restriction is x is greater than or equal to 2. And I included the greater than here because I didn't include it here. You just have to include it on at least one of them. And I should have written f of x up here. So now, what do you notice about the two equations from parts A and B? It's what I've been talking about. They have the same slopes, but they are opposite. One is positive 1, the other is negative 1. They also have opposite y-intercepts, and that's because of that plus or minus that we did. And the domain restrictions are opposite. So one goes less than -2, the other goes greater than -2. And speaking of, that should be -2. So x is greater than or equal to -2. So now finally rewrite f of x as a piecewise function. So f of x is equal to this absolute value function, which is equal to the two pieces. We have x plus 2, and then we have negative x plus 2. The positive slope is from x is greater than or equal to -2, and then the negative slope is when x is less than -2, because it's on the left side. All right, rewrite the following absolute functions as a piecewise. Okay, so a couple of things. When writing your piecewise, you need to figure out your equations. Sorry, your expressions. They're not equations. You need to find your expressions, and you need to find the meeting point, or points. There could be multiple, like in this example. Okay, so with this one, your parent function is going to be y equals x squared. That's our parent function. And we are applying two transformations. We have a horizontal translation and then that absolute value. So for this particular one, our expressions, if we take the absolute value, are going to be plus or minus x squared minus 3. These are the two expressions we're going to see in our piecewise. We're going to see a positive x squared minus 3 and then a negative x squared minus 3. So where are the domain restrictions going to change? Our parent function looks like this. But if we shift it down 3 with that minus 3 in there, it's going to look like this. Okay? And then when we apply that absolute value, it's going to take whatever is below the x-axis and it's going to fold it up to the top. Okay? So that means the folding points are going to be here, which means that's where our meeting points will be for our piecewise and how our domain restrictions will be set up. So to find out where those points are, I'm going to set whatever is inside the absolute value equal to 0. So x squared minus 3 is equal to 0. So we have x squared equals 3. When you take the square root within an equation, you have x is equal to plus or minus the square root of 3. So those folding points is going to be when x is equal to negative square root of 3 or x is equal to square root of 3. Well, and, not or. So when we set this up, f of x is going to be equal to, we're going to have 3 pieces, all right? The first piece is going to be on this left side here. This did not change, all right? It is not going to be folded up. Therefore, we want to use the function or the piece where the parabola is facing upwards. And that's going to be the function or the expression that has the plus. So the first piece is going to be x squared minus 3. However, this middle piece here, this will be reflected, all right? And if you think about it, once we flip that over, that parabola, that portion will be facing down, all right? Which means your expression should be negative. So it makes sense to use the negative for this one. So I'm going to distribute it. We'll end up with negative x squared plus 3. And the plus 3 makes sense as well because now your vertex for that is passing on the positive end, where it's +3, as opposed to before, it was passing through -3 down here. But since we flipped it over, we need to use that to show that reflection there. And then this last piece over here, this tail end, this did not change, all right? It was not affected by the absolute value. It was already positive, so we're going to use the positive parabola that was facing upward. So now the domain restriction. This left end, it did not change up until √3. So that tail end represents x is less than -√3. Next is this middle piece here, all right? That reflection happened from -√3 to +√3. And if you read your piecewise from left to right, make sure that your entire domain is covered. And then this last piece over here is going to be from √3. It's when x is greater than √3. So we've covered our full domain. We have -∞ to -√3, between -√3 and +√3, and then √3 to +∞. The last thing we need to do is include those reflective points, or the meeting points. And I just put them in the middle because it's easier to do that way. So this is our piecewise function. The last one is more analytical than graphical like I did over here. So let's just focus on finding the meeting points and then what expression we will use. So think about this. We have this absolute value function. I know that x is hanging out there, but let's ignore that for a second. We have this absolute value function. We have this part in here that's all positive, but now we are applying a vertical reflection, right? So this absolute value is not going to be facing upwards, it's going to be facing downwards. Okay, so we want to think about that when we are setting this up, okay? So I want to find the meeting point, so I'm going to set whatever is inside the absolute value equal to 0. So we have 3x is equal to 1, x is equal to 1/3. So with this one over here, for example A, we had 2 meeting points, which means we should have 3 pieces to our piecewise. Over here we have 1 meeting point, which means we will have 2 pieces for our piecewise. So f of x is going to be equal to, I'm going to have 2 pieces. Now, if I rewrite this as, rewrite it without the absolute value, but show all of the possible expressions, I'm going to have x. The x doesn't change. It's not in the absolute value. But now if I follow what I did here, where I did plus or minus x squared minus 3, I can rewrite this at, well, you can do minus plus or plus minus or minus 3x minus 1. And then these are my 2 potential pieces. So my first piece is going to be x plus 3x minus 1. My second piece will be x minus 3x minus 1. Now, if you want, you can distribute. You don't have to. You can combine like terms. I'm going to go ahead and do that, okay, so that we can kind of see exactly what the slopes are going to be. So with this one, I have x plus 3x. That's going to be 4x. And then minus 1. This one's a little bit trickier. We have x minus 3x and then plus 1. So we end up with x minus 3x, which is negative 2x, and then plus 1. All right, so now if I look at this, I know that my absolute value is facing downwards. I don't need the exact points to see that, but this first portion here has a positive slope, all right? And then since my absolute value is facing downward, I can see that this first portion here will be a positive slope. So that's going to be on the left side of my meeting point. So that means this first piece is responsible for when the x values are less than 1/3. And then on the other side, I can see that the slope is negative. So that means this -2 slope, or this second piece, is going to be responsible for the x values that are greater than or equal to 1/3, because this is 1/3 here. That is x equals 1/3. So on the left side, or when x is less than 1/3, is going to be a positive slope, which is 4x minus 1. On the right side, when it's negative, which is that -2, it'll be x is greater than or equal to 1/3. All right, that concludes Unit 1. This is just a table. You can look that up in the key. I'm not going to go through every single one. We talked about it throughout the lesson, but if you have questions, please let me know.